And howdy there, Calculus 2 students. We are looking at the Maclaurin series today. It is an extension of the Taylor series. In the Maclaurin series, instead of centering about 0, we're going to center about some point A. So it's just an extension, looks very similar to the Taylor series, where the Taylor series is centered at 0, our Maclaurin series is centered at A. And they tell us that we're going to need to know the values of x for which the power series converges, and this is known as our interval of convergence, which we've been looking at. And this next issue we'll talk about in a little bit. In example 1, we're going to find the Maclaurin series for the following functions and give the interval of convergence. So I'm going to need to write down these derivatives. Now it's not readily apparent to me that in example 1 they're asking me to do the Maclaurin series centered at 0. But evidently that is what they're asking. So that means I'm going to need to compute these values at 0. Alright, I've computed these values and written out the Maclaurin series as it appears above, and writing this in terms of my power series notation, that's going to be k beginning at 0 going to infinity. It's alternating, so it'd be -1 to the kth power, and then I would have this x to the, and these are all even powers, so this would be to the 2k power over, and these are all even, there, and that would be my power series. I also need to find the interval of convergence, so I'm going to need to do one of my tests. I will use the ratio test. It is my favorite, so I use it when I can. It's going to be the limit as k goes to infinity of that k plus 1 case over the kth case. So this is going to be -1 to the k plus 1. I'll write it all down. Alright, so this thing absolutely converges, and my r is less than 1. Therefore, my interval of convergence is from -infinity to +infinity. It's everywhere. Alright, going to go to the next one, and I'm going to need to compute those derivatives and those values, and we'll then put it together in our Maclaurin series. Alright, computing the function values there and the derivative values at that x equals 0. I write down my Maclaurin series and I get something that simplifies to this. And this, written as a power series, goes from x equals 0 to infinity of just x to some k. And this is a geometric series. We already know that this geometric series converges for x less than 1, so my interval of convergence is -1 to 1. In this next example, they want us to find the first 4 non-zero terms. So I'm going to compute the derivatives. It's centered at 8, and I'm going to go ahead and get those derivatives first, and then we'll plug in for the Maclaurin series. So here we are. I found the derivatives of all of those. Next I'm going to compute those values at x equal 8, and then we'll just chunk it into our Maclaurin series formula. Alright, now here goes. Let us assemble this Maclaurin series. I need my first term, that's a 2, plus, and then I'm going to have this 1/12 over 1 factorial. just going to write it like that. And x minus 8. And then I'll go ahead and just write minus 1 over 144 over 2 factorial. And then it's x minus 8 quantity squared. And then it'll be a plus 5 over 3, 4, 5, 6 over 3 factorial. And then times x minus 8 to the third. And it goes on and on and on. They just wanted me to write down the first 4 terms, and that is 4. So I can just simplify these numbers. Alright, there it is simplified. In example 3, they want me to find the Maclaurin series for f centered at 0. Well, I've already done that. We did that for the Taylor series in section 1. So I'll just go ahead and write down what that looked like. It was just 1 plus x over 1 factorial plus x squared over 2 factorial plus blah 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 plus x to the n over n factorial, and then we wrote that as a series by just saying that it was k equals 0 at the beginning, going to infinity of x to the k over that k factorial. So that one has already been done. Find the interval of convergence. Doing the ratio test for this, seems like we've done this as well. If you do the ratio test for this, you will find that your r ends up equaling, doing the k plus 1 case over the kth case, you'll find that you end up with this x over k plus 1, which we've already done as well, I believe. That means that my interval of convergence is negative infinity to positive infinity. So that's for A and B. Now the C part, that one is where we've got to move this, we've got to use what we have found before to try to get a Maclaurin series for all of these. Alright, so looking at this very first one, x to the 4th e to the x, I'm going to write this as x to the 4th, and I'll write the power series for this to infinity. We already know that this is x to the k over k factorial. So in combining this in to my power series, which I can do by those theorems that we looked at earlier having to do with the properties. Infinity, this is going to just be x to the k plus 4 because I add exponents when I multiply over k factorial. And then I'm going to write down what this will look like. Alright, that's what that one looks like. And the next one is e to the minus 2x. So let's write that down, e minus 2x. Now all I'm going to do is just replace my x's in this case with a minus 2x. So let's write down what that is by using that function composition property. So there's the general form with minus 2x substituted in. Now what I can do is break this apart by taking that negative out and putting that negative 1, k equals 0 to infinity, and then writing that negative 1 to the kth power. That way I can look at this as just a straight 2x to the k over k factorial, and I'll write down what those individual terms look like. Alright, there they are. Next, I've got e to the minus x squared. I'm going to use the function composition property again. Just substituting in to x, I'll substitute in minus x squared. So that's going to look like minus x squared raised to the k over k factorial. And simplifying that again, I'll take out the negative, and I will get this negative 1 to the k, and then I'll have left x to the 2k over k factorial, and then just writing down what those terms are. And there they are, just writing out the terms. Since the interval of convergence for e to the x is negative infinity to positive infinity, it doesn't change the interval of convergence at all. So the interval of convergence for each of these is negative infinity to positive infinity. Next, we're looking at a Taylor series expansion for binomial sequence and series. Our coefficients on that binomial expansion, here's what they're going to be for each individual term. And my binomial series expands as such. And we're going to look at our function f of x equals 1 plus x to the 1/2 power. So therefore p would be our 1/2. With p being equal to 1/2, our coefficients, our first coefficient would be equal to 1. Our second coefficient, or C1, would then be perform this operation right up here from 1/2 and 1. If I do that, I'll get 1/2 in the numerator, and I'll get 1 factorial in the denominator. This will yield 1/2. C2, or the third coefficient, would be 1/2 2. C3 would be equal to 1/2 3, and you'll just perform that computation. So writing this out, my expansion will look like going up here, 1 plus, my p is 1/2 x, plus my first coefficient was the 1/2, my second coefficient is then 1/8, and this will be x squared, plus, and then 1 over 16 x cubed, plus blah blah blah. Alright, so this is a binomial series centered at 0. Ooh. Note that they want me to approximate this, and what I did was approximate that, so that means this 1 plus x, so that would give me that x is 0.15. Plugging that in, I would get that p sub n of 0.15 follows this table. And there we go. If we just do one term, it will be 1. If I do these two terms, do 1 plus 1/2 times 0.15, I'll get this, and so forth. Alright, and the larger my n, the closer this value is to the real value. This is very similar to our last question, but with our p being equal to 1/3, and I'm going to expand this binomial series centered at 0. Alright, there they are. So the first 4 terms of this binomial series are 1/3 x minus 1/9 x squared plus 5 over 81 x to the third plus a blah blah blah. Alright, now I've done that. Use part A to find the first 4 terms of the binomial series for g centered at 0, where g is just some constant. So let's go ahead and write down what that g looks like in terms of my x with a c. Alright, so what I've done here is just pulled out the c so that I could write my function as function composition, and then I wouldn't have to do a whole new series. I could just look at this as my g of x being equal to what my f of x was, but replacing those x's with the x over c right in here. So I will have c to the 1/3 multiplied by, and it's going to be 1 plus 1/3 times x over c, just replacing that x with x over c, minus 1/9 x over c quantity squared plus 5 over 81 x over c quantity to the third plus a blah blah blah. Now this series would then converge for x over c being less than 1. In other words, my x must be less than c. My interval of convergence would then be from negative c to positive c. In part B, what they want me to do, part C, what they want me to do is take what I just found from G using this guy right here. So this is what I'm going to be using, and I'm to approximate the cubed root of 23. So if I want to approximate the cube root of 23, then I would go to something that I know, something that's close, and I'm going to look at this as the cubed root of 27, because I know what that is, minus 4. That would mean that my c in this case would be 27, and my x would be equal to negative 4. So for this one, I will just go in through here into this g of x, and I will plug in all of those values and do my number crunching. Similarly, for cubed root of 24, I'm going to do 27 minus 3, and this would mean that my c is 27, and my x is then negative 3, and I would plug that into my g. Now that's done for us in a nice tidy little table, and I'll get that for you. Alright, and here we are looking at this table. This is just the values for c and x equal negative 4 plugged in for each of these, and that approximation just using these three terms is what they say, or p equal to 3, which would be those 4 terms. Our absolute error, if we look at this, you can see that if we're really close to 27, our error is really tiny, and as we move away from 27, our error gets larger. Same way this way. So the closer you are to that actual value of c, and the smaller this x, the closer you get to the true value. Once again, we extend our definitions, this time of remainder, to include this convergence of the Taylor series and finding that remainder of that nth term. You'll notice that it is the n plus 1 term evaluated at, that's, well, not evaluated, is where I have that value of c, just as in the other problems. So they asked me to show that for the Maclaurin series it converges from negative infinity to positive infinity, so I do need to find that remainder, and then I'll show that convergence. So I know that this one, because we've looked at it before, converges from negative infinity to positive infinity, and this is my Maclaurin series for that e to the x. So my remainder of this nth term is then going to be the n plus 1 case, so that's going to just be e to the c. This is going to be my n plus 1 down here, and then times x to the n plus 1. Okay, and we showed this in a previous example. So now what we're going to do is we're going to take the absolute value, r sub n, just using the fact that, well, this is going to use the fact that e sub c is less than or equal to e, the absolute value of x for all n. We'll then have And now if we hold n fixed, we can find the limit of this as n goes to infinity for this remainder, this nth term of the remainder. This is going to be the limit. It's all of this stuff. And looking at this limit, I'm going to see that this doesn't depend on n, but this does. And the bottom is going to get bigger faster than the top, so this thing is going to 0. This means that this Taylor series is converging to e to the x, which is what we want. We want it to converge to e to the x because that's what it's representing. We're going to show that this Maclaurin series for cosine x converges to the function cosine x, and how we're going to do that is show that the remainder is going to 0, and if the remainder is going to 0, then we know this thing is converging to cosine x. So first up, let's write down our remainder. Alright, this is for a equal to 0, and my c is going to be somewhere in between 0 and x. Now do notice that all of my derivatives are going to be either sine or cosine, and that means that at 0, this derivative at 0, or sorry, at my c is then going to be bumping back and forth between 1 and -1. That means that my remainder can be said to be bounded. Alright, so there we have that it's bounded right here. This means that if we take the limit as n goes to infinity of this r sub n, we'll see that what we end up with is some x to the n over n factorial, and this is going to 0, and if the remainder is going to 0, we know that this is converging to cosine x. So this implies f is what? I'll write it down. And there we have it. And that is the end of 10.3.